Okay, so we're doing some more antiderivatives with integration, and let's consider our Euler's number derivatives. Okay, and so if I'm going to find the derivative of these ones, well, dy dx, if the derivative of this is just 3e to the x, it's the same, and then minus 2 goes away. Similarly here, is equal to, oh, that's just 3e to the x, and the root 5 goes away. And so you can see that derivatives are quite straightforward with e to the x. But however, let's pretend our original function is y, and we want to find the derivatives of this. We don't know what the constant is, so if I take my integral of this, y is going to be, well, the antiderivative of e to the x is just e to the x, because the derivative is e to the x times 3 plus c. In order to find the c value, I know it goes to this point. So if I plug in 17 is equal to 3e to the ln 5 plus c, well, I know that e to the ln 5, e and ln are inverses, so they cancel each other out. That ends up being 5 plus c. So this is 15, bring it over, so 2 is equal to c. And so my original function is y is equal to 3e to the x plus 2. And so we can, if we're given a point, we can actually find our constant c. If not, we just leave it as is. So let's try this particular problem here. The same idea. We're going to integrate e to the 2x. Well, when I integrate e, I know it is the same. But one of the things I have to be careful of is when I take the derivative of this, I have to do the chain rule. And so there's a 2x that has to be done. And so the derivative of 2x is 2. But I have to counteract that, so I have to divide by that coefficient. Similarly, if I do the next one, I have 6e to the 3x, because the antiderivative of e to the 3x is e to the 3x. But then I have to chain rule this. The derivative of 3x is 3, so I have to divide by that coefficient, plus c. And now I get 1/2 e to the 2x minus 2e to the 3x plus c. And if you're not quite convinced, if I come along here now and if I take the derivative of this, I get 1/2 e to the 2x times 2 minus 2e to the 3x times the derivative of that is times 3, and the c goes away. So there is my minus 6. These cancel out and I get e to the 2x. So we have to be careful of any kind of chain rule scenario in here, so that gets extra coefficients that we have to multiply the reciprocal of the chain rule's coefficient. Now this only works if this is a simple function. We'll try one more example here. We're told the derivative of f of x is this particular function, and we want to find f of x, knowing it contains this point here. Well, if I rewrite this, where I break up my fraction, I know it's 1/2 e to the 1/2 x plus 3/2 x to the 1/5. Okay, and so I also contains this point. So now if I take the antiderivative, f of x then is equal to, like, look at my function here first, that's e to the 1/2 x times the derivative of 1/2 is 1/2, and so that is considered here. I could have also kept this 1/2 here and multiplied by the reciprocal of the derivative, which is 2, which is also equal to 1. So either way you think about it works. And then I'm going to go, well, my 3/2, I add, this is not e, this is a power function, so, or a polynomial, so I'm going to add 1 to this, which is going to give me 6/5. I have to deal with my coefficient. I multiply by the reciprocal plus c. And so my function is e to the 1/2 x plus, well, this cancels to make it 2. I get 5/4 x to the 6/5 plus c. But I know it goes through this point here. So I know that when I plug in 0, I get -1/2. So e to the 1/2 times 0 plus 5/4 0 to the 6/5 plus c. Well, that's 0. E to the 1/2. 1/2 times 0 is 0. E to the 0 is 1. So it's minus 1/2 is equal to 1 plus c. And so now solving this, I subtract the 1 over, and so I get negative 1.5 plus c. And so my final function is f of x is equal to e to the 1/2 x plus 5/4 e to the 6/5 plus or minus 1/5, 1.5 is my function.